Hello everyone. Let us discuss about the topic control systems under the unit 2 of time response analysis. The topics are transient response, steady state response, steady state error constant system and type number. Objective. The main objective of this video lecture is to learn various methods of analyzing time response and also steady state error constant. Introduction. So control system are generally called upon to perform both under transient, that means dynamic, and steady conditions. So a feedback control system has the inherent capacity that its parameter can be adjusted to alter both its transient and steady state behavior time response. So what is a time response? The time response given by the system, which is a function of time to the applied excitation, is called time response of a system. So the total response is nothing but sum of transient response and then steady state response. So what is a transient response means? The output variation during the time it takes to achieve its final value is called a transient response. The time required to achieve the final value is called transient period. It is exponential or oscillatory in nature. So the next one is what is the steady state. So it is that part of the time response which remains after complete transient response vanishes from the system output. So it indicates accuracy of the system, that is steady state error, ESS. So next, this is a general second order transient response as well as steady state response. Here the transient response means having some oscillation and then settled. The final steady state is this is steady state. Okay. So this is a first order system. This one is a second order system. The first order system, this region is nothing but the transient response. So this region is nothing but the steady state response. So next, some of the standard signals are there. The first signal is step input, that is a position function, and then this is a step input for your given R of t. Okay, so this is a R of t is equal to A into U of t. So value changes from one level to another level, that is in zero time. In zero time. So U of t is equal to 1 for t is greater than or equal to 0. Suppose less than values, the negative values is equal to 0. So next one is a ramp, that is a velocity function which starts as the value of 0 and increases linearly with time. So whereas in the Laplace transform for the step input is A by S. Next ramp, this is a graph for ramp input. So here this is a ramp having the slope A and 1. Okay, that is a time is 1 and then this one is a R of t is A. So okay. Next, what is the R of t is equal to in terms of expression? A into t into U of t. So corresponding Laplace for this one R of s is equal to A by S square. Next one is a parabolic input, that is the acceleration. So this is a graph for parabolic input, where R of t is equal to A into t square by 2 into U of t. Taking Laplace transform, that will reflect here R of s is equal to A by S cube. So next one is a impulse signal. So unit impulse is defined as a signal which has zero value everywhere except at t is equal to 0, where its magnitude is infinite, also called as zeta. Also called as not zeta, there is a delta function. So delta of t is equal to 0 when t is not equal to 0. So integral in terms of expression for impulse signal is minus epsilon to plus epsilon delta of t into dt is equal to 1, where epsilon tends to 0. A perfect impulse signal cannot be achieved in practice. It is approximated by a pulse of small width but unit area. So the impulse function is derivative of step function. So Laplace transform of delta of t is equal to 1, which is equal to r of s. So the impulse response of a system with the transfer function c of s by r of s is equal to g of s. So what is a c of s? Becomes g of s into r of s, which is equal to g of s, because r of s is 1. So the impulse response of the system, inverse Laplace transform of the system transfer function. So this is where impulse response graph. This is for c of t, that is a inverse Laplace. So of c of s is nothing but inverse Laplace of g of s. This is nothing but g of t. Next, types of feedback control systems. The open loop transfer function of a unity feedback system can be represented in two forms. One is a time constant form and pole zero form. The time constant form is nothing but this one. G of s is equal to k into tau z1 s plus 1 and tau z2 s plus 2 etc. tau zm s plus 1 divided by s power n into tau p1 s plus 1 tau p2 s plus 2 etc. tau pm s plus 1 into e power minus tds. This is a time constant form. In terms of pole zeros form, so g of s is equal to k dash into s plus z1, s plus z2, etc. So s power n into s plus p1 into s plus p2, etc. into e power minus tds. This is a general pole zero forms. The gain in the two forms are related by k is equal to k dash of summation I zi summation j pg. Okay, so this is for general feedback system. Here I am giving the input is r of s. So this is for summer. So here having some generation of error. So because r of s minus c of s is nothing but error signal. This is a process g of s. So next is in time constant form, the term s power n in the denominator indicates the number of integrations in the systems. Okay, so g of s is equal to k into tau z1s plus tau z2s plus 1 etc. and similarly divided by s power n into tau p1s plus 1 tau p2s plus 1 etc. into e power minus tds. As s tends to 0, the integration term dominates in determining the steady state error. So the control systems are classified in accordance with the number of integrations in the open loop transfer function. When n is equal to 0, that means type 0 system. When n is equal to 1 means type 1 system. When n is equal to 2 means type 2 system. Types of a system means the number of poles, that is g of s, located at the origin. So next one, this is for g of s. So g of s is equal to k into tau z1s plus 1 divided by tau p1s plus 1. So this is nothing but here having s power 0. Okay, so that here s is not there, so that the system is type 0 system. So next one is, this is an example for type 1 system. So g of s is equal to k by tau z1s plus 1 divided by s into tau p1 s plus 1. Okay, here the s is presented, so that s power 1 is nothing but 1. So type 1 system, this is an example for type 1 system. This is the example for type 0 system. So g of s is equal to 2 by 5s plus 1 as the type 0 system. Whereas in the g of s is equal to 10 by s into 2s plus 1 is nothing but the type 1 system. So next, this is another example for type 2 system. So in general format, k into tau z1s plus 1 divided by s square into tau p1s plus 1. Okay, so this is second order system because the s to the power of 2 is how many number of poles located in the origin. Okay, so that is nothing but the type of the system. So this is the example for type 2. G of s is equal to 100 by s square into 3s plus 1. The closed loop transfer function T of s is equal to C of s by R of s, which is equal to G of s by 1 plus G of s into H of s. The denominator function is nothing but a characteristics equation which is equal to 0. The highest power in the s in the characteristic equation is called the order of the system. So the G of s is equal to k by s into tau s plus 1, where H of s is equal to 1. What is the C of s? You can substitute G of s by 1 plus G of s into H of s, so that the transfer function will be like this: k by tau s square plus s plus 1. This is a characteristics equation, so that which is equal to 0 means you can find the order of the system. So tau s square plus s plus 1 is equal to 0. The highest power in s is 2, so that the order of the system is 2. Whereas C of s by R of s, another example we can take it. So C of s by R of s is equal to 5 by 2s plus 2s square plus s plus 1. So this is a type 0 system and second order system. Type 0 second order system because the highest power in the s is 2. Okay. So next another example, C of s by R of s is equal to 10 by s into 2s plus 1. So here the s is presented. So how many number of poles are located in the origin means only once, because the s power 1 is s to the power is 1. So that type 1 system, the first order system. Okay. Next, poles and zeros of transfer function. The value of s which makes the transfer function infinity after substituting in the denominator of the transfer function are called poles of the transfer function. So the value of s which makes the transfer function 0 after substituting in the numerator of the transfer function are called the zeros of that transfer function. So the simple pole, that means real without repeated values, whereas repeated poles, that is a pole having same value twice or more than twice. Next, complex conjugate poles, a pair of poles which are complex conjugate values. So the given transfer function here is g of s is equal to 5 into s plus 2 divided by s into s plus 1. So equating the denominator, we can get the zeros of the transfer function. So equating the numerator equal to 0, we can get the zeros of the transfer function. So the s into s plus 1 is equal to 0, equating denominator is equal to 0. The poles of the transfer function s, one of the pole is 0 and another one is minus 1. So next here s 5 into s plus 2 is equal to 0. So the zeros of the transfer function is s is equal to minus 2. Steady state analysis. The steady state is that part of the output which remains after transients completely vanishes from the output. The steady state response specifications, settling time, time taken by the system to reach its steady state, that is a final value. It is also related to transient response because the same time will required by the transients to die out completely from the system output. The steady state error, the difference between the actual output and the desired output. So error ES is equal to R of s minus C of s into H of s. This is for non-unity feedback system. Whereas in the unity feedback system, E of s is equal to R of s minus E of s. It is also defined as the difference between the reference input and the feedback signal. That is the actual. So derivation of the steady state error. So you know this is R of s, this is the E of s. Here the output of the process is C of s. That is a feedback to the given H of s, and then the feedback signal is B of s. So next. So from the figure, so E of s is equal to R of s minus B of s. So what is the B of s? B of s is equal to C of s into H of s. So what is our C of s? C of s is nothing but G of s into E of s. So that you can substitute in this value in this equation. E of s is equal to R of s minus C of s into H of s. C of s is E of s into G of s. So you can take the E of s one side, so that E of s plus E of s into G of s H of s equal to R of s. So for you can get the E of s common for these two terms. So get it outside. So 1 plus G of s into H of s into E of s is equal to R of s. What is the E of s? R of s by 1 plus G of s into H of s. This is for unity feedback. So for non-unity feedback, whereas in the unity feedback system, so put H of s is equal to 1. Okay, that is E of s is equal to R of s divided by 1 plus G of s. So next, the steady state of the system is that the state which remains at t tends to infinity. That is, the steady state error is equal to limit t tends to infinity into E of t. The final value theorem, you know this. So limit t tends to infinity, f of t is equal to limit s tends to 0, s into f of s. Similarly, you can substitute the steady state error. So Es is equal to limit t tends to infinity into E of t is equal to limit s tends to 0, s into E of s. So for steady state error depends on R of s input signal and its type and magnitude. So and then G of s and H of s, that is the open loop transfer function. Substituting this E of s is equal to s into R of s by 1 plus G of s into H of s. You know this s, and E of s is equal to R of s divided by 1 plus G of s into H of s. So this is E of s is equal to limit s tends to 0, s into E of s. So that is equal to limit s tends to 0, s into R of s minus T of s into R of s. So next, steady state error for step input. So instead of you put R of s, you can A by s. So okay, so A by s, after you substituting A by s, so what is this? A by 1 plus limit s tends to 0, G of s into H of s, because A is a constant. So limit is not applicable for that one. So from the system, limit s tends to 0 into G of s into H of s, you can assume it as a positional error constant, that is Kp. Okay, positional error constant Kp. So that ESS is equal to A by 1 plus Kp. So this is where response for step input. This is where R of s is equal to A by S. So when ESS is equal to limit s tends to 0 into E of s, limits s tends to 0 into s into A by S minus T of s into A by S. So take it A is a common outside, 1 minus limit s tends to 0 into T of s. So next one is the ramp input. So instead of R of s, you can substitute A by S square. So after we can substitute A by S square and then rearrange, we can get ES is equal to A by limit s tends to 0, s into G of s into H of s. So for a system selected, this one is, you can assume this one is nothing but velocity error constant Kv. Okay, so what is ESS? A by Kv. This is for response for ramp input. Corresponding Laplace value is A by S square. So this is where ESS is equal to limit s tends to 0, E of s is equal to limit s tends to 0, s into A by S square minus T of s into A by S square. So A is a common for these two terms. You can take it outside. A into limit s tends to 0, 1 minus T of s by S. So next one is the steady state error for parabolic input. So parabolic means A by S cube. So that this is a response for your parabolic. So you can substitute this a by s cube in your ESS. So we can get finally ESS equal to a by limit s tends to 0 s square into g of s into h of s. You assume this as a acceleration error constant. So that Ka is limit s tends to 0 s square into g of s into h of s. So whereas ESS is equal to a by Ka. Next, this is a comparison table for various input with error coefficient and then steady state error. Okay, step. Whereas in you are applying the input as a step, so Kp is equal to limit s tends to 0 g of s into h of s. For steady state error is a by 1 plus Kp, and then steady state error for closed loop transfer function. ESS is equal to a into 1 minus limit s tends to 0 into t of s. For ramp, Kv is equal to limit s tends to 0 s into g of s into h of s. So for open loop transfer function, a by Kv, closed loop error steady state error is a into limit s tends to 0 1 minus t of s by s. For a parabolic, Ka is equal to limit s tends to 0 s square into g of s into h of s. For a steady state error for open loop, a by Ka, closed loop, ES is equal to a into limit s tends to 0 1 minus t of s by s square, where a is the magnitude of the input, t of s is the closed loop transfer function, g of s and h of s is the open loop transfer function. So the first problem, ESS, evaluate the static error constants for a unit feedback system having a forward transfer function. So estimate, that is a transfer function is this one, 50 by s into s plus 10. Estimate the steady state errors of the system for the input r of t is given by 1 plus 2t plus t square. Okay, so h of s is equal to 1. So that unity feedback. This is a first you can find the Kp. It is a positional error constant. Limit s tends to 0 g of s into h of s, which is equal to limit s tends to 0. You know g of s, h of s is equal to 1. So you can substitute. So after wherever you put s is equal to 0, that means infinity. Kp is equal to infinity. Kv is equal to limit s tends to 0 s into g of s into h of s. You can substitute g of s and h of s. So after that you wherever s you put 0, that means 50 by 10, which is equal to 5. Ka is equal to limit s tends to 0 s square into g of s into h of s. Limit s tends to 0, s get cancelled here. So remaining s is there, so that's 0. Okay. So next r of t is equal to 1 plus 2t plus t square, where this one is r of t is, this is where step input, this is where 2 times ramp input and then parabolic. Okay, the a1 value is 1, whereas a2 is 2, a3 is 1 again. So for error for the 3 input is ES is equal to a1 by 1 plus kp, a2 by kv plus a3 by ka. So you know already kp, kv and ka values. You can substitute this and find out the ESS value. The ESS value becomes infinity. So next, this is a steady state error for various input and system. Okay, various input and system. So whenever this one is the stable refers when the unit step input, the type 0 system has constant positional error constant, positional error constant, and then infinity velocity, and then infinity velocity and acceleration error constants. Okay, so whereas in the type 1 system, the system has 0 positional error and a constant velocity and infinity, that is a infinity position acceleration error constant. Acceleration error constants. Whereas in the type 2 system, 0 positional error, 0 velocity, 0 positional error and zero velocity, not a zero, infinite velocity error, and then having constant acceleration error constant at a steady state. So these are all the references I referred for preparing this video lecture. Thank you for watching this video.